So today we're going to start our next unit, which is called chemical nomenclature. Nomenclature is a fancy word for naming. Okay, so in this unit, we're going to learn how to name chemical compounds, and then we'll also learn how to write formulas for them. So to start off, just a quick review. So everything, like all of the materials, everything on our planet is made up of the elements. And there's about 100 that are naturally occurring. Okay, those last 18 on the periodic table, they're just man-made in like a science lab right now. So of those 100 elements, they can combine to make all of our different compounds. Okay, and sometimes they combine just like 2 elements at a time, like carbon monoxide. But you can have a lot of them that combine, okay, like sugars. Okay, think of like NaHCO3. So based off that, if there's 100 elements and they can make different combinations, how many elements are out there, you think? Or how many compounds are out there, you think? Like tens, hundreds, thousands, tens of thousands, hundreds of thousands. Okay, like a lot, right? Like thousands, probably tens of thousands, maybe hundreds of thousands. So if we have thousands and thousands of compounds to keep track of, do we have to have like a systematic way to keep track of them? We do. So originally scientists thought, well, maybe we could just like identify them based off their properties. But it turns out a lot of them are like silver metals or like white powders, and you would have to like, the list would go on and on. So scientists came to the agreement that each substance is going to be identified by its name and chemical formula. Okay, so again, this unit, it's the naming unit. Nomenclature is the fancy word for naming, and it is essential. Okay, you have to learn how to name compounds. You have to learn how to write formulas. It's how we're going to communicate both efficiently and effectively. So to start, we just have to know real basics about the periodic table. So the way elements are put on the periodic table, it wasn't random, right? So they're in there in a very purposeful spot. They're arranged according to properties, but also take a look at the atomic number on the periodic table. If you read it like a book, and what I mean by a book is we go left to right and then top to bottom. What do you notice about the atomic number as we go left to right, top to bottom? Okay, counts up by how many numbers each time? Just one. Okay, so we have them arranged so atomic number increases. And then you need to know what do we call columns and families. So this is where you should go to your first periodic table. Okay, so that first blank one. And I would just color in like one column. Okay, so columns are called groups or families. And then you can shade in any row. And then rows are called periods. Okay, so we talked about how columns are called groups or families. Well, if you look at the periodic table, there's 18 different columns. So we have to have a way to keep track of those columns. So each column gets a numbered letter combination. So on your second periodic table, go ahead and just label like the numbered letter combos. You don't have to shade in the columns, but you do need to know that the first column is called 1A. Okay, so just like this part. And then the second column, you just need to know the second column is 2A. And then I'm going to jump to 3A. So I'm going to jump all the way to where boron's column is. Okay, you need to know that column is 3A, then it goes 4A, 5A, 6A, 7A, 8A. Okay, so you just need to label those column names. And then for the B's, we don't do as much with the B columns. So if you don't want to label them individually, you can just kind of label this whole section. That's just the B section. Okay, we won't ever talk about like 3B, 4B, 5B. So you can just, this whole little chunk here is just the B section. So now we can take the periodic table and we're going to break it into just two big groups. Okay. Anything on the previous one you labeled with an A, we're going to call those representative elements. And you're going to find those on the outside of your periodic table. So I want you to actually shade in those columns. Okay. And those are representative elements. And then that section where we labeled as a B, those are called transition metals. Okay. And then notice on your periodic table, you have 2 rows at the bottom. Those bottom 2 rows are also going to be transition metals. Okay, so on your third periodic table, you're coloring those A columns or the outside edges one color, and make sure you're like color coding, that's your representative element. And then your middle section and those bottom 2 rows are called transition metals. The next way we're going to break up the periodic table is by metals, nonmetals, and metalloids. So first we're going to write down some properties of metals, nonmetals, metalloids, and then we'll color that 4th periodic table where they are. Okay. So first we'll talk about metals. So metals are going to be found on the left side of the periodic table, and we'll color it in a little bit so you can see where they're found. They have high electrical conductivity. So that means electricity can easily flow through metals. And how many of you have like shocked yourself when you touch something metal? Okay, so it's easy for electricity to flow through it. They have a high luster when clean. What is a high luster, or what is luster? Shiny, high luster, shiny. So luster is just like how they reflect light. So when metals are clean, they're high in luster, so they're like super shiny. Okay. They're ductile, which means you can draw them into wires. So if you were to look at like the inside of your cell phone or iPad charger, like this one right here, what's on the inside of this? What kind of wire? What kind of element? Who knows? What kind of element is made in these wires? Copper. Right, so like copper wires. They are malleable, which means they can be beaten into thin sheets. What kind of metal sheets do you probably have at home? Say it louder. Aluminum. Okay, so think like aluminum foil, right? So malleable, you can beat them into those thin sheets. And then it turns out like 80% of the elements up here, they are metals. So majority of elements are classified as a metal. Okay, and all of them are going to be a solid at room temperature except mercury. Okay, next we have our nonmetals. They are in the upper right-hand corner of the periodic table, except hydrogen. Hydrogen is a nonmetal, but where do you find hydrogen? Up here. Which one's hydrogen? Okay, top left, but it is a nonmetal. And these ones pretty much have the opposite properties, so they're poor conductors of electricity. So if you touch a nonmetal like the tabletop, are you ever going to shock yourself? And then they have like a low luster or like non-luster, so they're not shiny. Last, we have the metalloids. Metalloids are kind of the in-betweeners between the metals and the non-metals. So they have some properties of both metals and both non-metals. So like a big property we're interested in are like semiconductors. What does semi mean? What do you think, if it's a semiconductor, what do you think semi means? Good. Okay, what does this mean? Sorta, okay? So like semiconductors, they sorta conduct electricity like metals, not as good as metals, but then they do a better job than non-metals, okay? And they're kind of like that gray in between, right? So like there's not this hard line between metals and non-metals. Metalloids are kind of the in between. So now we're gonna go back to your 4th blank periodic table. And now you're just going to color in where the metals, the nonmetals, and the metalloids are. This one is hard to see, but the nonmetals are the top right. So this like goldish color are the nonmetals. The green are the metalloids, those in-betweeners, and then the rest of the periodic table are the metals. Okay, so you're going to color yours. I'd recommend maybe start with the metalloids. For whatever reason, historically, people kind of struggle with this section. And before we get into like naming metals and nonmetals, first let's just review some vocab. So atoms and ions are specific words. So if we use the word atom, we mean that it's electrically neutral. If we use the word ion, we mean it's electrically charged. And then remember, there's two types of ions. We have cations and anions. Turn to your neighbor and tell your neighbor, what is the difference between a cation and an anion? Okay, what's a cation? Okay, positive charge. What's an anion? Okay, negative charge. In this unit, when we talk naming, we're going to talk a lot about the cation versus the anion. Do you absolutely have to know cations are positive charged, anions are negative? Okay, if you don't, should you be rewriting this in your notes? Yes. Okay, so metals tend to become cations. So if metals become an ion, they're a cation. So does that mean they have a positive or negative charge? Positive. Okay, so metals will get positive charges. So an example, I'm just using Na with a plus. What's the name of Na? Sodium. Okay, so sodium, if it becomes an ion, it gets a plus charge. And then here's our first naming rule. It's the easiest one. Okay. The name of the cation stays the exact same name as the element. Okay. So for example, Na is, if you just look at the periodic table, what's the name of Na? Sodium. Okay. If sodium becomes an ion, it gets a plus charge. The name doesn't change. So sodium neutral is the same thing as sodium ion. Just kind of a side note, you don't have to write this down. So even though the name doesn't change, there are huge differences in the properties between the neutral metal and the ion metal. Okay. So for example, sodium, plain neutral sodium reacts violently with water, so it'll like maybe possibly combust. I'll demo for that for you later when we do like a unit on families. Okay. But then sodium ion is just stable in water. Think table salt. If you put some table salt in water, what happens? Nothing. Literally, it just dissolves. Nothing. Okay. So even though we call them both sodium, they're very different, right? This one just dissolves in water. Nothing exciting happens. This one catches on fire in water. Okay. So just kind of keep that in mind. Even though the name is the same, they're very different. Okay. Next, let's talk about nonmetals. So nonmetals are going to form anions. So what kind of charge do anions get? Negative. Okay. This time we have a different rule for naming. Okay. So when anions form, we change the name. And this is really simple for naming rules. We keep the root part of the name, but then we drop the ending and we add "ide." So, for example, sulfur, if it's neutral, we call it sulfur. But then if sulfur becomes an ion, it becomes sulfide. So I'll write that below. So just regular neutral sulfur. And then if sulfur becomes an ion, it'll get that -2 charge, and we change the name to sulfide. Okay, another example, like chlorine becomes chloride. What about bromine? What do you think bromine's going to become? Okay, bromide. What about fluorine? What's fluorine going to become? Fluoride. What about oxygen? Oxide. What about phosphorus? Phosphide. Good. Okay. So anions, we change the name. It gets that "ide" at the end. The last thing I want to talk about today are just these things called diatomic molecules. What does di mean? Two. So there are 7 elements that exist in pairs, meaning like physically, they cannot exist as like a single atom by themselves in nature. Okay, so you do need to write down these 7. As we're doing naming and formulas, this unit, you need to know which 7 these are. So what that means is there's no such thing as just like one single bromine atom. hanging out in nature. It is always found in a pair, so you'd write Br2. Okay. Same thing for iodine. There's no such thing as just a single iodine atom hanging out. It's always paired up with another, so it's I2. So if you want, go ahead and copy these. These are the 7 naturally occurring ones. And then we're going to add a few notes on the bottom. Okay, so these 7, you have to just get to the point where you've memorized them. Okay, so then let me show you a couple different techniques to remember them. I put them in this order on purpose, like the bromine, then the iodine, then the nitrogen. So if we write them out in that exact order, if we were to just kind of like put the letters together and say the word, it comes out to say Brinkelhoff. Everyone say Brinkelhoff. Okay, say it again. Okay, only 3 of you are saying it. Everybody say Brinkelhoff. Okay, Brinkelhoff. My number 1 technique. How do you remember these 7 elements? You have to remember the word Brinkelhoff. And do you see if you spell them out, do you see how it's now making them? Okay. The other technique I have, there's 7 of them. And if you look at them on the periodic table, do you see how they pretty much make a figure 7? Plus, the hydrogen is over here. But you can also remember, they're the ones that make a 7 on the top right corner. Okay. Additionally, do you have your periodic tables out? Okay, if you look at the back side, flip it over. The bottom left. Do you see the bottom left? I give you the list of those diatomics also. Okay, so they're here for you. The problem with just relying on the back side of your chart, if it's not crossing your mind, is it going to cross your mind to check the bottom left of this chart? Okay, it's not. So you have to kind of be mindful of Brinkelhoff, and you have to know this when we're writing formulas. Now the rule, it only applies when these elements are not bonded to something else. Okay, so I'm going to use oxygen as my example. Okay, so if oxygen is just hanging out by itself, how many of you have been to the hospital and you see the oxygen tank? Okay, what formula is on the oxygen tank? Is it just O or is it O2? Okay, it's O2. There's no such thing as just a single oxygen atom hanging out. It's always paired up. Okay, so when it's just oxygen by itself, it's O2. But then this diatomic rule doesn't apply when it bonds to something. So for example, what's the formula for water? Okay, H2O. Notice, now that oxygen is bonded to hydrogen, do you see how it no longer has to have that 2 there? Okay, so this rule is only when it's by itself, not bonded.